Hello, everyone, and thank you for taking the time to hear about aerospace experimental payloads. Today, I'm going to be talking about our mission to do suborbital and atmospheric missions for solar and materials research. So, our mission, AXP partners with research professors and government organizations, especially NASA, to do important experimentation in space and in the upper atmosphere. We do a lot of STEM outreach in the community as well, especially as part of the greater UNL Aerospace Club. But historically, AXP in particular has provided middle school and high school students opportunities to directly contribute to our projects. This was especially the case during our push for Big Red Satellite. And I'll just give you a good understanding of our past work we've done as a club. This picture here was our project from last year. It was for this bottom bullet point, this high altitude student platform. It was an 8-hour high altitude balloon payload flight. Um, I'm actually going to bring us back up to this top point, this Big Red Satellite 1. This was the first cube satellite developed in Nebraska. It was developed by our club, Aerospace Experimental Payloads. Um, and it was a collaboration with at the time, it was the National Renewable Energy Lab up in Boulder, Colorado. It's been since renamed to National Lab of the Rockies. Uh, And they do a lot of research on this new solar panel technology called a perovskite. It's just essentially this unique crystal structure that captures that can generate solar energy from kind of a different waveform. It's coming into use now in some new Garmin watches. They'll advertise that they can solar charge indoors, and that's thanks to this perovskite technology. And we as a club are, as far as I'm aware, the only research group studying their viability in upper atmosphere, long duration tests for aerospace purposes. Uh, So that big red satellite, it was launched up in a Falcon 9 rocket, went up to the ISS, and they essentially just opened up a window and threw it out. There's probably a lot more technical way of describing that. That's a very, they did it the right way. Yeah, so we had a CubeSat up in low Earth orbit for a couple days, and it just evaluated the long-term stability of these perovskites. We took a little break from that afterwards. We did the National Eclipse Ballooning Project, and that was during the 2024 total solar eclipse. So, only time we could do this. So, it was a super exciting opportunity. That's what this picture on the right is. This was just after letting go of the balloon. So, the balloon looks small as it gets higher up in the air. The pressure decreases, so the balloon expands until it eventually pops. But um, in the middle here is the parachute that will deploy once the balloon pops. This pink box had our experiment in it. Uh, and there's the big camera arm with a 360 GoPro camera on the end of it. And a little fun thing we did on the side, this box below it, it was full of little balloons full of paint. So as it got really high up in the air, those balloons expanded and then eventually popped. It made a pretty little painting. It was kind of cool. Um, and then last year we did this high altitude student platform payload. Again, it was meant to be, we called it a Big Red Satellite 1.5. It was kind of meant to be a successor or a stepping stone up to a progress, maybe another satellite. So this was a long duration, high altitude balloon flight done through NASA's high altitude student platform. So if we go back up, it was this big rig of a bunch of different payloads. Ours is this beautiful looking one right there with the big old N for knowledge. These black squares are those perovskite solar cells. There's a little nubbin right there. That's a sun angle sensor. And on the reason that this flight was so important was because for the Big Red Satellite 1, the sun angle sensor, it malfunctioned or something went wrong with it, so they couldn't get data for it. And this time on our altitude balloon flight, it did work. So fun data there. Um, yeah, and that was launched out of the Columbia Scientific Ballooning Facility out in Palestine, Texas. This year, We're going big. We're doing the RockSat program with out of Wallops Flight Facility in Virginia, and it will our we created a payload that's going to launch into space uh, this summer, so in June. Um, and it's not quite a satellite as the Big Red satellite was because that went into up in space and then into orbit. This one is going up on a sounding rocket, so it goes straight up and then straight down. So the line for space is 100 kilometers. That's the Kármán line. Our rocket is going to go where they're projected to bring it up to 180 kilometers. So we'll have a good 5-10 minute window exposed to space. So I'm excited for that. This is, I think, the same rocket. This year they said we're going to get higher than last year did. So I'm curious if they updated the rocket. Um, yeah, it's a two-stage rocket. It's a Terrier Malamute. That's it. Um, so once it's up in space, the top um, fairings of the rocket pop off, exposing all our payloads to space. Look, this is the picture from last year. Um, there are however many just shelves like this for payloads, and you can either get the full shelf for a ton of money, or half shelf or a quarter shelf. Um, Here I'll talk about. Sorry. Uh, yeah. And our experiment is in partnership with the Nanomaterials Lab here at UNL, led by Dr. Lee Tan. Um, and then we have a grad student who we're working super close with. His name is Grant Meyer. He's brilliant. Any questions you have, direct them to him, not me. I don't know what's going on. Um, and essentially, we're studying how atomic oxygen down here on Earth likes to be in pairs of two, but up in the low Earth orbit, the sun blasts it, so it gets into single, we call atomic oxygen, and it's incredibly reactive. So for when you have just kind of microcircuitry up in space, it can sometimes bond to those molecules and dope it, and then all of a sudden that molecule is not quite what it used to be, and might have different properties, and that's a bad thing. So we're looking into um, different ways to shield for that. So we're especially focusing on fluoropolymer films containing organic coating. So using these fluoropolymers to coat the electronics and protect them from atomic oxygen. The way we're measuring those qualities is using a method called broadband dielectric spectroscopy. It's a non-destructive way to track molecular scale degradation and shielding properties of fluoroethylpropylene. The fluoroethylpropylene is what we're using to coat our electronics for this flight. And our mission is to demonstrate a compact, low-power, broadband dielectric spectroscopy payload architecture that is suitable for future materials and diagnostics missions. Here's our payload design. Left here kind of shows how everything works together. Um, it's on a shelf like this because our experiment is actually so small in form factor. They decided so that they could fit as many experiments on the sounding rocket as possible. We have I mentioned the different shelf sizes. We are special quarter shelf. So we are New Jersey Tech has their half payload, and we put this little shelf to go over their electronic section, and our payload slides in beautifully. These little chips, they're called interdigitated electrodes. They have just wires like this, and we send an alternating current into this end, and then um, the fluoropolymer coating resists that electric field generated through that impedance, and then it sends the same current back on the other end, and then we measure the impedance of that. It uh, Whatever. Oh, shoot, I spoiled it. Um, Yeah. So our sensor, it generates a real and an imaginary number, which this is all, we use those two numbers to find the capacitance of the substrate. And then through all this magic, I call it magic, we turn it into dielectric loss. And we're expecting from our measurements these two different peaks. This is a dielectric loss versus temperature here. This first peak, shoot, I put a note. I forget. It's so this beta, this first peak is the localized, and the second one is the segmental relaxations of the material. And the beta is because of the side group motion of in the fluoroethylpropylene at lower temperatures, and the alpha is the backbone segmented motion at higher temperatures. That's what our grad student told me in a Discord message, so I trust. I'm the software engineer of the team and electrical. So to make this all work, we're using the analog devices AD5933, which is just this little chip. And it's an old chip. Luckily, these analog sensors, they have a long lifespan of usability. But we actually had to make our own breakout with an analog front end to it. So this chip, it sends out the signals that we needed to, and then it reads as we needed to, but it's not, there's a lot of essentially formatting you have to do to get it to perform our experiment correctly. So we had to design this chip ourselves here in KiCad. So it's been dubbed the AXP 805933. If you want one, let me know. We have extras. Um, yeah. So this chip on its own, it can't turn. The chip sends out the alternating frequency, but then it comes back out as the same voltage because nothing's causing the voltage to step down. It just is carrying an impedance. Um, and we need this analog front end to essentially turn that into some measurable change in current. I think so. We have an op amp over here that does that. Yeah, that's what this baby is. Um, and this blue chip is it manufactured and all soldered together. We also have barometric altimeter right here. And then as a kind of redundant system, we also have a inertial measurement unit, which we're going to take the Y acceleration and just integrate it twice, and that gets us altitude as well. So we're excited to see how well these match. And then another engineering challenge, I'll put it back in presenting mode. Another engineering challenge, clack. Another challenge we had is that these impedance sensors, they only have one I2C address. So essentially, that's like we have 5 sensors. It's like having 5 kids and they're all named Gus. So if you were to say, hey, Gus, go clean your room, there's going to be a question on which Gus you're talking about. And they might all do it at the same time, and that's hard to keep, you can't keep track of that. So the solution we have is we have a multiplexer here, which allows our microcontroller. We're using a Teensy 4.1 because it has this super fast clock rate and then built-in SD card to make it easy for us. Our computer uses this multiplexer to be able to refer to one at a time. And we're able to, even with the multiplexer, they're still essentially on one I2C bus, so you can't truly run them in parallel, but we're able to give the command to this first board to say, hey, start sending this current out and doing your frequency sweep stuff so you can get the number back. And then before it's finished doing the measurement, we switched the channel to tell the second one to do the same thing, third one, fourth one. And by the time we finished telling them all to start their reading, this original one is finally done doing its work. So we're able to ask it, hey, what'd you get? And then it tells us the reading that it got. So by pipelining the different times that each sensor is busy, um, we're able to essentially run them in parallel, which is super exciting. There's a lot of embedded code work that went into this project, and that's what gets me excited. Um, when we are measuring the impedance of our samples, which will clip into these little white chips, um, there's going to be some gain factor to it that we need to account for to kind of get an objective measurement. So we have this switch here, and for the first 75 seconds of launch, or before the launch, while we're on the pad, it we're essentially going to be measuring from a known resistor. So it's not soldered on the board in this picture, but I have it labeled gain calibration resistor. So it will be measuring from that resistor, which will have a known resistance and capacitance, so that when we switch using this black box onto our sample, it will have that offset to apply to it so that we get the correct numbers. The RockSat rocket provides power to us at, it was 28 volts plus or minus 4. So we use buck converters to step that down to the 5 volts the TNT expects. And the rocket also provides a timer event line that we're going to use as a signal to our computers that say, hey, we're about to lose power at the end of flight, or we low-key might burn to a crisp if we stay on. So it sends a 28-volt signal, which we step down to 3.3, so that we can bring it into a digital input pin of the TNT to have that digital signal to say, hey, time's up, let's wrap it up. Another software thing we had to fight, another hurdle was that saving data to an SD card, any sort of kind of interaction with memory like that, or like long-term memory like that, it's a relatively slow operation for a computer to do. And for such a small window of time where we're in space going to be taking our most valuable measurements, we don't want to be busy saving information to an SD card. So what we do, and this is pretty standard also, we save all of our data in a buffer in RAM on the computer, just in the chip. So not the SD card, but closer memory that's a lot faster to talk to. Especially, it's particularly on this TNC, it's split up into two areas. There's the regular RAM, which is just for like math computation, you having something on the side, you know. Um, and then the second RAM is direct memory access RAM. And that RAM is optimized so that when the SD card tries to pull the information, it can be done really quickly. So we buffer it and then push it to the SD card as few times as possible. We have that run every 70 seconds. Yeah. Here is how we apply our, fluoryl ethyl propylene D onto our electrodes. We tried a spray coating, but we found that to be um, not quite even. So we dip it instead, and that worked out very well. And we use ellipsometry to measure the thickness and verify that it's nice and smooth. Here's a graph. Here's another pretty graph. Here's a pretty picture. And all this work is made possible by the NASA Nebraska Space Grant, the UNL College of Engineering, the BRS CubeSat Foundation, and then our wonderful Aerospace Club advisor, Dr. Rachel Wagner, grad student Grant Meyer, and Dr. Lee Tan, and then Dr. Yaning Soon. She is the expert at ellipsometry, which we use to make those chips. Here's us the day we finished manufacturing our board, late night, but had a lot of fun. Future work, big things are happening. Some of our freshmen just got accepted, or our club, Space Dynamics Laboratory and the U.S. Air Force reached out to our club with for a call for proposals to participate in their satellite design program, and we got accepted with a research project that builds on this year's, where we are applying our learnings to neuromorphic computing in space. Um, so think AI. We're hitting all the buzzwords. Um, yeah, we're excited for that. And then next year, we're gonna continue our collaboration with the National Lab of the Rockies, formerly NREL, to do more research on perovskite solar cell technology for aerospace applications. Thank you for taking the time to listen to our talk. Um, Email me if you have any questions. I appreciate your time. Have a nice day.